but don't get us confused with the electronic music, dance music producer who goes by Chandroid. So the background of our project has been the increasing desire to use mobile devices throughout the US government, spanning all parts of the government. And with that increasing desire to be able to use mobile devices, there's been an increasing interest in Android because of its open nature. It's an open platform, it has increasing market adoption. And so for many of the same reasons that we were interested in Linux previously, we have an interest in Android, because it gives us the freedom to extend it to meet our particular needs and to then seek to get those extensions adopted based on their technical merit. And of course, in particular, the motivation for security-enhanced Android is the need for improved security in mobile operating systems in general. So SE Android is first a project in which we are seeking to identify and address what we perceive as the critical gaps in the security of Android today. And initially, the project is beginning by enabling the use of SE Linux in Android, based on our expertise in having created SE Linux originally and our belief that SE Linux will in fact make a significant difference to the security of Android. But the project is not intended to be limited in scope to SE Linux alone, so we do intend to expand the scope of the effort as we go along. And then secondly, SE Android is a reference implementation being produced by the project, which will provide a worked example of the security enhancements that we are proposing. And so initially, the reference implementation that we released last month is a worked example of how to enable and apply SE Linux to Android. Some of the use cases for security-enhanced Android are listed here. The first is to prevent privilege escalation by apps, whether those would be actual malicious apps that you might download from the market, or whether it might be a privilege escalation from exploitation of a flaw in a legitimate app on your device, like the browser. We also hope to be able to mitigate the threat of data leakage by apps through the security enhancements in SE Android, as well as to prevent bypass of various forms of security functionality that might be on the device, whether that would be VPN software that you might have on the device, or antivirus software, or any other kind of security functionality that you're relying upon on the device, ensuring that that security functionality is in fact unbypassable and can't be trivially subverted. SE Android also has the potential to enforce legal restrictions on data, whether those would be restrictions on classified data, as in the Defense Department and intelligence community, or whether it would be for compliance requirements in various industries. And then lastly, SE Android use case is to protect the integrity of the applications of the data on the device. And so the intent here is that SE Android would provide benefit across a wide set of markets and users, everything from consumers through the corporate enterprise to the government. Because we know that in order to get these adopted into mainline Android and to make them available in commodity devices, they have to be applicable to all these market segments. So in considering SE Android, it was important for us to first fully grapple with the notion that Android, while being Linux-based and Linux-derived, is quite divergent from a typical Linux. And that's come out in many of the prior talks. Almost everything above the kernel is different, from the Dalvik VM runtime to the application frameworks, and even the low-level C library and init program and system daemons differ. And although the kernel is, of course, based on Linux, even the kernel differs, and it differs in important ways. Android has added new subsystems to the kernel, and those new subsystems introduce new ways for applications to communicate with each other, and new ways that they might potentially escalate access. And so that then introduces new issues that have to be addressed to secure the system. So today, Android provides a two-layered security model. At the upper layer, there's the application level permissions model, and this is the model that most Android users are familiar with. This is what controls the ability to invoke various system components, various app components, and to control access to system resources like the Bluetooth subsystem or the use of networking sockets or the SD card. And so these permissions are what the app writers specify in their manifests up front, and these are the permissions that are seen by the users. But in addition to that user visible permissions model, there's also a kernel level model, and that kernel level model is foundational to Android security because there's an assumption that any app can potentially come with native code. And so the kernel provides strong sandboxing and isolation in order to ensure that the application level permissions model can't be bypassed. But it does so in a way that attempts to be invisible to users and app writers. So as I mentioned, the application isolation sandboxing is enforced by the Linux kernel in Android, and it's explicitly stated in Google's documentation that the Dalvik VM is not a security boundary. Any app can run native code, and thus you can't rely on the Java layer, in particular anything that runs in the application space, for security. And so today, what Android makes use of is Linux discretionary access controls based on UIDs and GIDs and permitted bits. So discretionary access control is the typical form of access control in Linux. And it gets its name from the fact that access to the data is entirely at the discretion of the owner or creator of the data. And that doesn't just mean the human user of the data, but rather the program that's being executed at the time. Also, characteristic of discretionary access control is that some processes, typically UID 0 processes, can override the model completely, and some objects are unchecked by the model. And so these are based on user group identities, and it tends to be very limited in its granularity and have a very coarse-grained privilege model that's prone to escalation. So in the particular case of Android, it makes use of discretionary access control in two ways. The first is to control use of system facilities by applications. Now, in most cases, the applications get access to system resources indirectly. They perform an RPC via the binder to the system server, and the system server provides access. But in some cases, the applications directly access kernel resources. And for those situations, Android defines a set of groups that control access at the kernel level to limit things such as Bluetooth access or network access or the SD card. And so that requires special purpose kernel mods for the Android kernel to enforce that, since a normal Linux kernel doesn't know anything about specific group identifiers. And then more traditionally, Android makes use of discretionary access controls to isolate the apps from one another. And so every time you install an app on your device, it gets a unique user group ID allocated for that app. And that gets assigned to all the processes representing that app and all of its files as a form of a boundary between that app and any other app on the device. What this tends to lead to, though, since discretionary access control wasn't really designed with this kind of model in mind, is a very hard-coded and scattered policy. If you look through the Android source tree, you'll find specific user group identifiers hard-coded and specific modes hard-coded into various header files, and then also scattered throughout various configuration files. And so it becomes essentially impossible to show any kind of properties about the effective policy being enforced on the whole system. SELinux is a mandatory access control scheme for Linux as contrasted to discretionary access control. And so what that means is that first it enforces a system-wide security policy that covers all of the processes and objects on the system, not just a subset of them. And it's based on security labels that can encode additional information about those processes and objects. Information such as the function trustworthiness of the code that's executing, or the role or classification of the process or the data. And so in particular, what SELinux can do that's not normally available through discretionary access controls is it can confine flawed and malicious applications, including even ones that run with UID 0. And it can also prevent privilege escalation with respect to user space. So the ways in which SELinux can help Android are first, it can confine the various daemons that run as root on Android today. Today, any flaw in any one of those daemons is fatal to the security of the entire device. SELinux, in contrast, can help protect those privileged daemons from misuse and can limit the potential damage that can be done via them. SELinux can also help provide a much more rigorous way of sandboxing and isolating the apps from one another, in which the separation covers all objects and operations, not merely a subset of them, and it's safe against various forms of privilege escalation. And then lastly, SELinux brings the benefit of a centralized analyzable policy as opposed to a scattered and hard-coded one. At the same time, it's important to understand what SELinux can't mitigate. First, in general, SELinux cannot mitigate kernel vulnerabilities because it's a kernel-level access control mechanism. Now, in some cases, SELinux can and has blocked exploitation of specific kernel vulnerabilities by making those particular code paths unreachable, or by limiting the damage that might be done. For example, some kernel vulnerabilities might expose setuid programs to exploitation. And in an SELinux system, the setuid applications are no longer all powerful. But in general, we can't guarantee protection against all kernel vulnerabilities at the SELinux level alone. And then secondly, SELinux can't mitigate anything you allow in your security policy configuration. And so that really emphasizes the importance of having good policy. And it also points out the importance of application architecture, because the extent to which you can use something like SELinux to protect the system depends to some degree on how well the applications are designed, particularly the system applications. And so decomposition of applications and application of least privilege principles in developing them are still very important. So the goals for SE Android as a project are first, to integrate SELinux into Android in a comprehensive and coherent manner, spanning the kernel up through the Android user space and dealing also with the upper layers. Secondly, we want to be able to demonstrate actual useful security functionality in Android using SELinux. Functionality of interest not only to the government, but also to consumers and business. As we go through the process, we expect that we will find aspects of SELinux that are not well suited to Android, potentially in terms of resource utilization or in terms of the unique usage model of Android. And so we hope through this process to begin to identify the issues that are real versus those that are perceived, and to begin to overcome any issues that are there. And then lastly, in the project, we're seeking to, as well as address SELinux, also identify and address other security gaps that exist in Android. So enabling the use of SELinux in Android requires overcoming a number of challenges in all areas. At the kernel, when we began this work, there was no support for per-file security labeling. And since SELinux access controls are based on security labels, this limited the granularity of protection that we could provide. Also, as I mentioned earlier, since Android adds its own unique kernel subsystems, and those kernel subsystems are used to communicate between apps, they ultimately have to be instrumented in order to be able to enforce any kind of security policy on an Android-based system. In the case of the user space, we've done a lot of work in the past to integrate SELinux support into Linux distributions. So a lot of work has gone into integrating with the GNU utilities and other aspects of Linux user space. But since Android has its own unique user space, very little of that carries over into an Android environment. Also, given that Android provides a rich set of framework services for sharing and interactions among apps, and not all of those interactions are directly visible at the kernel level, at least not at the granularity you might want, that also poses some challenges for applying SELinux to an Android-based system. And then lastly, in the arena of policy, over the years, an extensive reference policy has been developed for SELinux. But that reference policy has been developed for conventional Linux distributions. So once again, it's not well suited to Android, and it also wasn't really designed with size in mind. And so it's grown to a significant size to cover an extensive array of different Linux programs, whereas on a resource-constrained device, it doesn't really fit. So in the kernel space, we've overcome the challenges I mentioned before. First, of course, there's the simple matter of just enabling SELinux and its dependencies in the kernel. That's relatively straightforward. In the case of per-file security labeling, the YAFIS2 file system, which is the standard file system for raw NAND storage, has actually gained support for extended attributes in recent years. And so with a fairly minor modification to the YAFIS2 file system code, we have full per-file security labeling for YAFIS2. Also, for devices that are using ext4 or similar type file systems, those already provide the necessary security labeling support, since that's long been provided for in the Linux distributions. And then we've done some analysis of the Android binder subsystem, and we've added security hooks and SELinux permission checks to it, so that we can in fact enforce access control policies over binder IPC interactions. In the user space, we've taken a minimal port of the existing SELinux user space over to Android. And here we focus on adapting SELinux so that it will run cleanly on Android. So for example, adapting from the GNU C library to the Bionic C library, as well as making sure that we only port over the essential parts needed to run on the device so that we have as small a footprint as possible. We've also taken the various tools for generating file system images so that the SELinux security labels can actually be initialized when you build the file system images, rather than having to first create images and bring the system up once and then apply labels after the fact. We've also done some work recently to integrate SELinux into the recovery and updater subsystems. So the talk yesterday, which went into some significant depth into the Android OTA software updater mechanism, was very timely. And we likewise had to extend the release tools, the recovery console, and the updater program to provide security labeling support. And then we've gone through various key parts of the Android user space and extended them appropriately for SELinux so that they can make use of SELinux and properly label processes and objects. We also created a set of JNI bindings for the SELinux API so we can expose this up to the framework services and, if necessary, to the apps. And we've created some simple examples of extensions to the settings app to provide some basic capability for managing certain SELinux settings. On the policy side, we've created a new policy from scratch, tailored specifically to Android and written with footprint in mind. And so we have a very small policy, particularly in comparison to the policies you'll find in Fedora or Red Hat or other Linux distributions, which confines or locks down the various daemons and also lets you limit the apps. And does so in a way that doesn't require us to keep adding new policy as you add new apps to the system, so it scales well. In particular, we've made use of SELinux's existing multi-level security support in order to isolate the apps from one another in a very simple manner. And we've introduced some new extensions to SELinux policy to particularly deal with the issues of how to label apps on the system. But a key aspect here is we've gone out of our way to make sure that the app writers for Android never have to see SELinux policy, because we don't expect them to understand or want to understand SELinux policy, or for the user to want to trust the app developers to create policy for their own apps. And we've gone out of our way to make this invisible to users, except to the extent to which a user wants to interface with it through something like an optional menu on the settings system. So this slide gives a quick synopsis of our current footprint for the boot system recovery partitions. We don't have any footprint on the user data partition. So these are sizes of the image files that are produced by a build for the Nexus S phone. And so for the boot partition, it shows here we had a 140K increase to the boot image size. And so that's essentially the increase for the kernel size to turn on SELinux and its dependencies, plus the policy files to bootstrap the system, plus the extended init program. The system partition increased only by 48K here. And that's basically the size of the SELinux library, extensions to the toolbox, and the small set of extensions we've made to things like the JNI bindings and the framework services. And the recovery image here goes up by 152K. It used to actually be the same as the boot image, as you might expect, because they share much in common. But it's gotten a little bit larger now because of our integration with the recovery console, the updater program facility, so that when you apply an update, those also get labeled properly. So currently what we have is a working reference implementation that we've open sourced. And this work began before Ice Cream Sandwich was open sourced. And so when we first started our work, we were working on the Gingerbread branch on the 2.3 series. And we continued to work on that up through 2.3.7. And then when Ice Cream Sandwich was released, I guess last November timeframe, we ported over to Ice Cream Sandwich. That only took one developer less than 2 days to bring it forward. So that was very straightforward, which I think reflects both on the fact that the changes aren't that extensive and the code we're dealing with has a certain level of maturity in Android where we're making our modifications. And so we've been tracking the Android open source project master branch, the tip of that. So we're essentially 403 plus subsequent changes. And we've been testing our reference implementation. We started out working on the emulator because that's a very nice development environment and a good way to bootstrap. And then since then, we've also brought up on the Nexus S phone as a sample phone device and the Motorola Zoom tablet since we ported to Ice Cream Sandwich. And since we released it publicly last month, we've had users on the outside report success using it on the Galaxy Nexus phone as well. Now, we still see a lot of work that needs to be done to get to what we would consider to be anywhere near a complete solution. But we wanted to step back and sort of assess, does this in fact make any difference for real vulnerabilities? And so we did some analysis. And actually, much of this analysis occurred while we were still working off of Gingerbread before we made the leap to Ice Cream Sandwich. So we looked at an exploit and a vulnerability for the Android volume daemon, or VOLD. So this is a daemon that runs as root on the device, and it manages the mounting of disk volumes, like the SD card. And then in Ice Cream Sandwich, it also takes on a role for the encrypted file system storage. And it gets messages from the kernel notifying it of things like when an SD card is inserted or removed. Unfortunately, a vulnerability was discovered in it in which it was not, in fact, checking the message origin. And so not only could the kernel generate these messages, but other processes, including unprivileged apps, could generate these messages and forge them. And worse, it took a signed integer out of the message that it received over these netlink sockets, and it used it as an array index without checking to see if it was less than 0. So pretty easy to turn that into an arbitrary code execution exploit as root. And so that was demonstrated on the outside by the Gingerbreak exploit. So the way Gingerbreak works is once it's running on the device, whether that's because the user themselves is running it to try and root their own device, or whether it's gained code execution through some flaw in some existing app, like say the browser, and is starting execution there. First of all, it surveys the phone to collect all the information it needs to carry out its exploit. And so it finds the volume daemon process on the device. It collects up the addresses and specific values it needs to create its malicious payload. And then it generates a carefully crafted message that it sends to the volume daemon process that will ultimately create a return to libc attack. It'll execute its own exploit binary from the volume daemon's process, and so now it's running as root, at which point it can create a setuid root shell, at which point at that time or any time later, you can execute that setuid root shell and it has root. Game over. So our question was, would SA Linux have helped with this vulnerability and exploit? And would it have made a difference just using the sample policy we developed before we read anything about this vulnerability and exploit? Just a policy developed based on normal Android operation and policy development practices for SA Linux. So at the first stage, the exploit finds the volume daemon process on target. And so to do this, it uses the proc file system. So it reads various information out of the proc file system. And one of the things it does is it goes through the various proc PID directories until it finds a command line that matches the volume daemon. However, in SA Linux policy, typically we don't allow one process to read the proc PID entries of a process running a different security label. And so this was denied by the policy we had developed before ever reading anything about this exploit. And so the existing exploit as written would have failed right off the bat at the very beginning. But we'll give the exploit writer some credit. We'll assume that if he knew he was going up against an SE Android, he would have recoded it based on some other means, or he would have used a brute force attack. Doesn't really matter. We'll just assume he can get past this phase. So at the second stage of the exploit, the attacker, the exploit itself, is trying to find out specific addresses it needs to create the malicious payload and specific values. So it reads various files off the file system. It also makes use of the Android's logging subsystem to get some very helpful fault information. And so here again, the default policy we created, just based on normal policy development practice and operation, would have blocked its access to some of the files that it needed to get all the information it needed to create the payload. And so again, it would have failed here at the second stage. But again, we'll give the exploit writer some credit. We'll say that knowing he was going up against SE Linux, he would have perhaps preset the addresses based on some information about a static build, or he would have done more brute forcing. We'll just let him get past that. So at the third stage, the exploit, having gotten all the information it needs, it now actually creates a netlink socket and sends the message to the volume daemon. Except there's no legitimate reason for unprivileged code to be creating this kind of netlink socket or sending on it. And so this was not allowed by the default policy we created in the beginning. And so here the exploit again fails. And there's really no way for the exploit writer to get around this one. If you can't send on this netlink socket, you can't reach the vulnerability in the volume daemon. And so this is a complete block. But we don't like to frustrate exploit writers, so we'll give them a fighting chance and we'll allow this permission, just to see what will happen. So at the fourth stage of the exploit now uses a return to libc attack to trigger execution of the exploit binary by the volume daemon itself. But again, there's no reason for the volume daemon to be executing anything outside of system, ever. And so, and he can't write to system at this point, and so he can't actually execute his exploit binary. So again, he would fail. But again, we'll say he knows he's going up against SE Linux, maybe he knows what policy he's going up against, and so he'll recode the exploit so he doesn't have to actually execute a separate binary off the disk or off the file system. He'll just do it all in memory. So at the fifth stage, the exploit actually creates a setuid root shell. And to do this, it does two things. One, it remounts the data partition to clear the no suid flags, because otherwise the setuid root shell doesn't do anything there. And then secondly, it chounds and chmods the file to make it setuid root. Neither one of those things are a normal operation for volume daemon on a normal Android system. And so again, the policy we had written blocked this, again, without having known a priori anything about this vulnerability or exploit. But again, we'll give them a fighting chance and we'll allow this to proceed. So at the last stage of the exploit, it actually executes the setuid root shell, and so now it has UID 0. Well, who cares? Because the SE Linux security context on the process hasn't changed, so he's still limited to the same set of permissions by SE Linux. He has no super user capabilities, and so while he seems to have succeeded, he didn't actually gain anything going through all of that. So in conclusion, for this vulnerability and exploit, SE Linux would have stopped the exploit in 6 different ways during its execution path. It would have forced the exploit writer to tailor the exploit to the target up front based on prior knowledge, rather than being able to dynamically survey the device once he's already on it. And it made the underlying vulnerability completely unreachable. And all vulnerabilities that fall into the same class, which there have been other such vulnerabilities on Android and elsewhere. All right, in the interest of time, I'm going to actually skip past this next one, but you can read it yourselves. The slides will all be available. But we surveyed several other root exploits and studied them. And what we found is, for many of these different root exploits for Android, SE Linux would, in fact, have made a difference, and it would have blocked them from succeeding, often in many different ways. Again, just based on normal Android operation and policy development practice. Now, a lot of times these root exploits are used by users to simply gain ownership of their device so they can reflash it. And that's not really what we're trying to prevent here. But the problem is that these same root exploits that are sometimes being created by users for ownership of their own devices are also then getting picked up into malware. So the Gingerbreak exploit I mentioned earlier actually did show up in malware in the wild, in the so-called Gingermaster malware. So now we'll look at a different kind of issue. Rather than talking about root exploits here and privilege escalation attacks, we're going to look at the question of app isolation from each other, which, as I mentioned earlier, Android just uses discretionary access controls for. So in the past year, it came out that the Skype app for Android very conveniently stored sensitive user data without encryption with full readable permissions in its data directory, with little things like your account balance, your date of birth, your home address, your contacts, your chat logs, and everything else it got its hands on, where anything else running on the phone could grab that information and leak it. Not so good. But this is really a classic example of discretionary versus mandatory access controls. In discretionary access controls, the permissions are left to the discretion of each application. And so all it takes is one careless application writer to get things wrong. With mandatory access controls, the permissions are defined by the administrator, whoever creates the policy, and they're enforced uniformly across all applications. So you don't have that problem. And so with the policy that we define for SE Android, all apps are in fact denied read access to files created by other apps. And that's done by having a unique MLS category set on the app process and its files. And that's not up to the app writer. And so careless app writer doesn't matter. It's still blocked. So you might say, well, that's just because the Skype app developers made a careless mistake, but I'm sure no one else makes mistakes like this. Well, a simple survey of the public literature shows that the same class of vulnerability has shown up in many apps. And what's interesting is these apps that are listed here come from the security community and the banking industry, two communities that we hope are paying a little bit of attention to security. So if they can't get security right using the existing security model, then we don't have much hope of anyone else doing it either. So the conclusion of these case studies was that, in fact, Android security would benefit from SE Linux. And more generally, that Android needs some form of mandatory access control and not just discretionary access controls. And that in particular, SE Linux would have mitigated a number of Android exploits and vulnerabilities that have shown up. Now, all that I've described thus far has been limited to enabling SE Linux in its use at the kernel level, for the kernel level objects and operations. We have done a little bit of work to instrument the Zygote as well, and a few permission checks there. But what we haven't yet done is lift that up into the actual application frameworks. And so to really protect against malware and flawed apps, you also need some notion of mandatory access control for the Android permissions model, the higher level model that I mentioned earlier, that is in fact visible to the users and the app developers. And that requires extensions to the Android frameworks. Now, there has been some work in this space. There's a paper at last week's Network and Distributed Systems Symposium towards taming privilege escalation attacks on Android, where there's a group of folks out of Darmstadt University, I believe, that have done some work on trying to provide some kind of mandatory access control scheme at the Android permissions level. And so something like that ultimately needs to be created, and we're actually planning to continue our work and work our way up the stack and do so in a way that integrates well with the SE Linux controls that we have at the kernel level. Unfortunately, the code from the paper I cite here is not publicly available, so we can't directly learn from it. So we created this reference implementation, we did this analysis work, and we actually talked about this project first at the Linux Security Summit last year, before we released any code. And so then we made our first release of the reference implementation that I mentioned January 6th, so last month. And not long thereafter, we then took the patches, cleaned them up some, improved the changelog summaries, and actually submitted them to the Android open source project. So those are actually visible in the Garrett server, Android review server on Google Source. And so those have been uploaded and submitted for consideration to the Android open source project. And the patches for the Bionic C library actually have already been merged. The other patches we've gotten some feedback on from the Google Android developers. And so there's been some coding style cleanups. We've wrapped our changes with conditionals so that at least currently it's easy to compile all of this in or out. And we're continuing to work through that process and seek to get this mainlined. Because our goal here is not to maintain our own fork of Android, but rather to bring these security enhancements into the mainline so that they can ultimately find their way out into commodity devices, just as we did with Linux previously, in getting that adopted into enterprise Linux systems. So what's next for SE Android? As I mentioned, we're going to continue our work to upstream as much as we can to the Android open source project. We don't know ultimately how that will turn out, how much they'll take, but so far they've been very good about giving us constructive comments, and they haven't identified any fundamental stumbling blocks so far, and so we're continuing to work toward that end. As I mentioned earlier, to fully address the problems of flawed and malicious apps, we do need a mandatory access control scheme at the higher layer, the higher security model as well. And so we plan to tackle that as well, and we have some ideas in that space. Right now, what we have has a very simple mechanism of essentially generating policy at image build time. And so what we need to do is management. So we envision some work there, for example, to extend the device admin APIs that are currently used to manage various aspects of Android, things like password restrictions or requiring encryption or disabling the camera, and extend those facilities so that an enterprise can easily provision Android devices with their particular policy requirements, as well as continuing to improve the settings app support for consumers to make use of. There's still work to be done in integrating SE Android throughout the entire stack. There's other Android-specific kernel subsystems that we still need to review and potentially instrument. There's still other aspects of the Android user land that need further review and potential extension for SE Android. And then, as I mentioned originally, we do still plan to ultimately look at other aspects of Android security beyond SE Linux and begin to address those gaps as well. So we have a project wiki, and so the URL is there. And that provides information about how to get the code, how to build it. Please understand that this is not targeted at most Android users, right? This is really targeted at developers, power users, and ultimately it's really targeted at getting it upstream. But if you are comfortable building your own Android images, then everything you need is available there. And we encourage people who have questions and comments about it to bring them to our public mailing list for SE Linux. That's listed there. If you want to have a private dialogue about SE Android and you're not comfortable taking it to the public list yet, then you can send email to our team alias or to me specifically. And we welcome your feedback and